In section 8.5, we are going to derive the sum and difference formulas, and then we are going to apply those formulas to solve problems. Before we actually do the derivation, before we look at where the formula comes from, let's just look at what the formula says. So it's really an interesting formula. It says that the cosine of alpha plus beta, or of a plus b, is equal to something a lot different than what you would think. It's equal to the cosine of a times the cosine of b minus the sine of a, the sine of alpha times the sine of beta. The difference formula is very much the same. The cosine of a minus b is equal to the cosine of a, or the cosine of alpha, times the cosine of beta, plus the sine of alpha times the sine of beta. So if you're looking for a way to keep the formula straight, a couple things to think about. You're going to take the cosine of a and the cosine of b. You're going to take the sine of a and the sine of b. And the sine here is the opposite of the sine here in both the formulas. Notice that in the cosine formulas, the cosines are together in the beginning, the sines are together in the end. The sine formulas, the sum and difference formulas for sine, are kind of the opposite of the cosine formulas in two different ways. So if we have the sine of a plus b, that's equal to the sine of a times the cosine of b. See what I mean by that difference there? And then it's also plus, and then we switch and find the cosine of a times the cosine of b. The cosine of a times the sine of b. There's the switch. So you can probably figure out that the sine of a minus b is going to have a subtraction sign in the middle, and everything else is going to stay the same. So it's the sine of a times the cosine of b minus the cosine of a times the sine of b. Next, we want to look at where a couple of these formulas actually come from. If you take a few minutes to look at this picture, what we have here is an angle, and that first tiny little angle right there is b, or beta. And then this bigger angle right here is alpha. So this point right here is on the unit circle. And so the coordinates of that point are the cosine of that angle beta and the sine of that angle beta. We're going to call that point P1. This point over here, because this big angle is alpha, it has coordinates cosine alpha and, cosine alpha and sine alpha. We're going to call that point P2. What we're going to do next is take this triangle, this angle, let me change colors for a minute so you can see what I'm talking about. This angle right here would be the angle alpha minus beta, right? Because this whole big thing is alpha and this little thing is beta. And so if we subtract beta from alpha, we get alpha minus beta as this angle in between. And what we want to do is redraw our x and y axis and redraw our unit circle. And we're going to kind of shift this triangle around a little bit so that this side sits on the x-axis And so this angle in here is the angle alpha minus beta. And so this point here, which we're going to call P3, has coordinates cosine of alpha and sine alpha minus beta, and the sine of our angle, which is alpha minus beta. All right, so what we really want to look at here is this triangle, and then when we shifted that around, we have this triangle. Those are the same triangle, and you can actually do a little bit of calculation and use the side angle side, because we've got this side congruent to this side, we've got this angle congruent to this angle, and then we've got this side congruent to this side, so the two triangles are equal. What we want to do is use the distance formula. This point here on the x-axis is point A, and its coordinates are 1, 0, because it's on the unit circle, and we want to use the distance formula to find the distance from point A to point P3. Because these are the same triangle, this is going to be equal to the distance from P1 to P2. So in our first triangle, the distance from here to here is going to be equal to the distance from here to here. So we're going to use the distance formula and set those two things equal to each other. Remember that your distance formula is x minus x squared and y minus y squared. Right? So over here on the left, we're going to have the cosine of alpha minus beta. So this is our formula from this triangle. Should probably do it the other way. So we got the cosine of alpha minus beta minus 1. I'm sorry, so it was the cosine of alpha minus beta minus 1 squared plus the sine of alpha minus beta minus 0 squared. Okay, so that's this y minus this y, this x minus this x. And then from this triangle, we're going to get cosine of alpha minus cosine of beta squared, right? So here's cosine alpha, that's my x, minus my x. And do my y minus my y. So this will be plus sine of alpha minus sine of beta squared. Right, if I square both sides of my equations, I get rid of my square root. So I'm going to have the cosine of alpha minus beta minus 1, that's still squared, plus the sine of alpha minus beta. The minus 0 goes away, that's still squared. On this side, I've got the cosine of alpha minus the cosine of beta squared plus the sine of alpha minus the sine of beta squared. I'm going to do a bunch of foiling. I've got 4 different things that are squared. And so when I do that FOIL, this is going to end up being the cosine squared. And I'm going to change to A's and B's because I think they're easier to read than alphas and betas, but they mean the same thing. So I get the cosine squared of A minus B minus 2 cosine A minus B plus 1 plus the sine squared of A minus B minus 2 sine of a minus b whoops, sorry about that. This second piece here isn't a FOIL. We're just squaring, think of this as like a variable here. We're just taking the sine of something squared. And so that's all it's equal to. It's equal to the sine squared of a minus b. So if you look here, I've got a cosine of a minus b plus a sine squared of a plus b. So that whole thing is equal to 1. I'm going to add that to this other one here. So I've got 2 minus 2 times the cosine of a minus b. On the other side of the equation, I'm going to end up with, in this next step right here, I'm going to end up with a cosine squared of a minus 2 cosine of a cosine of b plus cosine of b squared plus sine of a, sine squared of a, minus 2 sine a cosine a plus sine b sine squared of b. So cosine squared of a plus sine squared of a is 1. Cosine squared of b plus sine squared of b is 1. And then I've got minus 2 cosine a cosine b minus 2 sine a cosine a. I can subtract 2 from both sides of my equation. So the 2's will go away. I can divide everything by negative 2. So that negative 2, that negative 2, and that negative 2 go away. And I end up with the cosine of a minus b equals the cosine of a times cosine of b minus the sine of a times, whoops, wait, did I make a mistake here? I did. This should have been a sine of a. Nope, wait a minute. Minus 2 sine a, that should have been sine b. So this is sine b right here. So minus sine of a times sine of b. And that is one of our rules that we started out with. Okay, so now that we've established that identity, we can use it to help us find exact values of things that aren't in our unit circle by turning things into things that are in our unit circle. So, for example, if I want to find the exact value of the cosine of 75 degrees, I can rewrite 75 as the cosine of 45 degrees plus 30 degrees. Right, then our formula tells us this is our A and this is our B. So this is going to equal the cosine of A times the cosine of B minus the sine of A times the sine of B. Right, and as you're doing these problems, you want to be starting to memorize your formulas. Remember that what I think about with cosine is that it matches in words, but it doesn't match in sign. And then the sum and difference formulas for sine doesn't match in words, but does match in sign. All right, so if we do this with our values we have here, we have the cosine of 45 degrees times the cosine of 30 degrees minus the sine of 45 times the sine of 30. And so those are all unit circle values. So we've got square root of 2 over 2. Let's see, cosine is the x-coordinate, which is way out here in a 30-degree angle. So that's times the square root of 3 over 2 minus the square root of 2 over 2 times a half. And if you do the math and simplify that, let's see what we're going to get. We're going to get square root of 6 over 4 minus the square root of 2 over 4. We could leave this like that. The online program might want you to factor out that 1/4 and call this square root 6 minus square root 2. Next problem is going to work similarly. So we want to be thinking about a way to write pi over 12 as some of the values that we know. And this one is a little bit trickier. If you think about 12, some of the factors of 12 are 3 and 4 and 6. So if you start thinking of some of the things in your unit circle, right? So you think about pi over 4 would be 3 pi over 12. Pi over 3 would be 4 pi over 12. Oh, and right there is something that's going to have a difference of 1 pi over 12, right? So cosine of pi over 12, we are going to rewrite as the cosine of 4 pi over 12 minus 3 pi over 12. So there you can see that that's equal to 1 pi over 12. But then let's simplify these so that we recognize them. So that's going to be the cosine of pi over 3 minus pi over 4. Okay, so the formula for this one is the cosine of A, so the cosine of pi over 3, times the cosine of pi over 4, opposite sign, so this is plus the sine of pi over 3 times the sine of pi over 4. Pi over 3 is kind of up top in our unit circle. Its cosine is a half. Pi over 4 is a matchy-matchy. Sine of pi over 3 is square root 3 over 2. Sine of pi over 4 is square root 2 over 2. So if we simplify this, we've got square root 2 over 4 plus square root 6 over 4, which if we simplify it like we did the other one, we're going to get 1/4 times square root 2 plus square root 6. Now, if you look at example 2 in the book, they happen to come up with two different numbers that subtracted to give you pi over 12. They actually used 3 pi over 12 and 2 pi over 12, which reduced to pi over 4 and pi over 6. But those will give you the same answer as we ended up with here. It was just a different way to get there. Another thing that you can do with your difference formulas is that you can use them to find new identities or to prove new identities. So we've been asked to prove that the cosine of pi over 2 minus theta is just equal to the sine of theta. That is our co-angle identity. Remember, pi over 2 is equal to 90. And we know from before that the cosine of 90 minus an angle is equal to the sine of that angle's complement, right? So this is an identity we already know, but we're just going to use our difference formula to prove it. So we're going to rewrite this as the cosine of pi over 2 times the cosine of theta, and then opposite signs. So this is going to be plus the sine of pi over 2 times the sine of theta. See, pi over 2 is up at the top, so its x-coordinate is 0 and its y-coordinate is 1. So the cosine of pi over 2 is 0. And so 0 times cosine of theta is also going to equal 0. The sine of pi over 2 is 1. And 1 times the sine of theta is just going to be the sine of theta. And so 0 plus the sine of theta is the sine of theta. In example 3, we're going to do the same thing we've been doing. We're going to try to figure out how to use our sum or our difference identity to find the sine, the exact value of the sine of 7 pi over 12. Hopefully you've already realized that this would be 3 pi over 3 pi over 12 plus 4 pi over 12, and that those guys are going to reduce to known values. So remember that sine is different in words, but it's the same in values. So it's plus with sine, and in writing down the formula, sine comes first. So this is going to equal the sine of 3 pi over 12 times the cosine of 4 pi over 12 plus, because remember plus matches, the sine of 4 pi over 12 times the cosine of 3 pi over 12. All right, so if we simplify this, 3 pi over 12 is pi over 4. So the sine of that's going to be square root 2 over 2. The cosine of 4 pi over 12 reduces to pi over 3. So the cosine of pi over 3 is a half. The sine of pi over 3 is square root 3 over 2. And the cosine of pi over 4 is square root 2 over 2. So this simplifies to square root 2 over 4 plus square root 6 over 4. And once again, we can factor out the fourth, and we should get an answer that looks something like that. You can also use these formulas backwards. So if you look at this example, you should recognize, oh look, I've got sine cosine minus cosine sine. That looks like my difference of signs formula. Remember that the sine of A plus B, no, minus B, so the sine of A minus B was equal to the sine of A times the cosine of B minus the cosine of A times the sine of B, which is the pattern we have there. So we've got this, and we're going to go this way. So this is going to end up being equal to the sine of 80 degrees minus 20 degrees, which is the sine of 60 degrees, which is a unit circle value, and the sine of 60 degrees is just equal to the square root of 3 over 2. In example 5, we are given two angles and some information about those two angles. So we know that the sine of angle alpha is 4/5. So be thinking opposite over hypotenuse. And angle A is going to be in the second quadrant because it is bigger than pi over 2 and it's less than pi. So if we think about drawing that guy, it's going to look something like this. Here's our angle alpha. Since the sine is 4/5, we can think of our y-coordinate for this point being, we can't really think about it being 4/5. What we want to think about is that for this angle, we've got the opposite is 4 and the hypotenuse is 3. And because this is one of our special right triangles, one of our Pythagorean triples, we know that this side down here is going to be equal to 3. And this guy over here was angle A. Angle B is bigger than pi and less than 3 pi over 2. And so he is going to be over here in quadrant 3. Okay. So angle B comes around here like this, and since opposite over adjacent is -2 over 5, the length of this side is 2, right? This distance is -2, but the length of the side is actually 2, and the hypotenuse is square root 5. So if we wanted to find this third side, we would take square root of 5 squared minus 2 squared equals that side squared, so the length of this side up here is just going to be equal to 1. All right, so in example 5, they want us to find 4 things. They want us to find the cosine of alpha. They want us to find the cosine of beta. They want us to find the cosine of alpha plus beta. And they want us to find the sine of alpha plus beta. All right, so the cosine of alpha is going to be relatively easy from our picture. It is going to be adjacent over hypotenuse, and so our cosine is just going to be equal to -3 over 5. Because remember, we're over here in the second quadrant, so even though we've got this marked because that distance is 3, that coordinate is going to be -3, so our cosine is -3 over 5. The cosine of angle B over here is going to be our adjacent side of 1, which is also a negative, divided by the square root of 5. And we can rationalize that guy if we want to. If we want to find the cosine of alpha plus beta, we're going to use our new identity. So we're going to find the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. We found the cosine of alpha in part A. So we got -3 over 5. We found the cosine of beta in part A, so we got -1 over the square root of 5. Minus the sine of alpha, which was given, times the sine of beta, which was also given. And I'm going to let you simplify that. And I'm also going to let you figure out part D on your own. It's just the similar process. Use your formula. You already know the values that you need to know to answer that question. In example 6, we are asked to establish an identity. That means we're being given an identity that is known to be true, but we have to show that it's true. So when we do this, what happens is we start out with the information given on the left side, and we only work on the left side. So we don't actually know that these two things are equal yet. That's what it means when it says to establish the identity. And so I like to put like a little question mark here with my equal sign, because that reminds me that I cannot do the same thing to both sides of this equation because I don't yet know that they're true, okay? It's kind of like if I had x plus 7 is equal to 2 plus 9, I don't know that that is true yet, right? If I know that x is equal to 3, then this thing is not true. And because it's not true, adding something to both sides doesn't give me something that's equal because it didn't start out as equal. So what I do when I'm trying to establish an identity is I start out with what's known, and then I try to work my way to the thing that I'm trying to prove. So the obvious thing when I look at this to me is, okay, well, look, I've got my difference of cosine values, difference of angles here. And so I'm going to write that out with the formula. And so that's going to be equal to the cosine of A times the cosine of B plus the sine of A times the sine of B. And I can already kind of see where this is going to be maybe not easy, but some interesting things are going to happen. So I'm going to distribute the division. This whole thing is divided by the sine of A times the sine of B. But, well, here, let me go ahead and write it for you. So it's divided by the sine of A times the sine of B. But that means that I divide both parts of this by the sine of A times the sine of B. So I end up with the cosine of A times the cosine of B over the sine of A times the sine of B, plus, see how I'm going to have sine of A sine of B over sine of A sine of B? So that's just going to be plus 1. Cosine alpha over sine of alpha is going to be equal to cotangent of alpha. Cosine beta times sine of beta is going to be equal to cotangent of beta, and then plus my 1. So now I've established the identity. So you see what I did? I started on this side, I did things to this side, and I eventually got that side to be equal to the thing that I was looking for. That's what you do when you establish an identity. So we have so far gone through the sum and difference formulas for sine and cosine. There are also sum and difference formulas for tangent, but we're not going to do very much with those two yet. But we are going to at least look at them. So the tangent of A plus B is going to be equal to the tangent of A plus the tangent of B over 1 minus the tangent of A times the tangent of B. The difference identity changes signs everywhere, okay? And so I'm going to show you this with a different color. I'm going to put a minus here. So the tangent of A minus B is equal to the tangent of A minus the tangent of B over 1 plus, I think my OneNote is about to die. Hold on. Let me pause the recording. Well, we lost everything in the crash, so we'll write it down again. The tangent of A plus B is going to be equal to the tangent of A plus the tangent of B divided by 1 minus the tangent of A times the tangent of B. The formula for tangent of A minus tangent of B is almost exactly the same, except that the signs are opposite. So the tan of A minus B is equal to the tan of A minus the tan of B divided by 1 plus the tan of A times the tan of B. And you might have a few problems in the homework where you have to use that. If you're interested in the proof, in the old version of the book, the green book, that proof starts on page 643. In our last two examples, we are going to solve some trigonometric equations that are said to be linear in sine and cosine. That means we have equations that have both sine and cosine in them, but neither of those is squared or cubed or anything like that. So we say that they're linear. In example 11, we want to solve the sine of theta plus the cosine of theta is equal to 1. And we want to find all the solutions that are in the interval from 0 to 2 pi. So when I look at this equation, what occurs to me is that sine squared of theta plus cosine squared of theta would be a nice thing to be able to get. So maybe what we want to do is square both sides. So if you think about foiling on the left, you're going to end up with sine squared of theta plus 2 sine theta times cosine theta plus cosine squared of theta equals 1 on the right. Sine squared plus cosine squared is 1. So if I subtract that 1 from both sides, I get 2 times the sine of theta times the cosine of theta equals 0. Can divide both sides by 2. And then I've got something times something equals 0. And we've been working with that forever. So I need the sine of theta to equal 0, or I need the cosine of theta to equal 0. So where does that happen in 0 to 2 pi? Sine is equal to 0 when our y-coordinate's equal to 0. So that happens at 0 and pi. And cosine of theta equals 0 when our x is equal to 0. So that happens at pi over 2 and at 3 pi over 2. But because we squared both sides of the equation, we might have created some solutions that don't work. So you want to go back and check each of these in the original equation, and when you do, you're going to find out that pi is not a solution and 3 pi over 2 is not a solution. And so theta is going to be equal to 0 and pi over 2.